with a large 22-digit number. This is 22 digits, not hard to verify. And this number is formed by just, I guess you could say, concatenating the odd integer starting with 11 and ending at 31, but it is a 22-digit number, which is fairly easy to verify. So this is 22 digits, a good sized number. And you may be asking, well, why don't you just divide powers of 3 by manually? And you could, I guess, but that's not the best approach. I think we all agree on that. So this is a 22-digit number. All right, and note that if k is equal to 0, it automatically divides it. 3 raised to the 0 is 1, and so we know that k might be equal to 0 if we can show that 3 does not divide this number. Now this little lemma right here turns out to be pretty important. It's fairly obvious, but just in case, it really holds basically because 3 to the k will always divide, just by laws of exponents, 3 to the k will always divide 3 to the I if I is greater than k. And again, we're talking about non-negative integers usually here, I think, or always. So 3 to the k would divide 3 to the I under these circumstances where I is an integer greater than k. And that's just clear from properties of exponents, and just you can think like 3 cubed would divide 3 to the 4th, right, for example. Now let me get this to fit. Okay, so 3 to the k divides 3 to the I, which is essentially why this statement is true. Okay, now another important result right here is that these two congruences, any power, any non-negative integer power of n is going to be congruent to 1 mod 3. For example, you could think of 10 squared, that's 100, minus 1 is 99, and 3 divides 99, right? And similarly for 10 to the n is congruent to 1 mod 9, okay? And again, we're interested in these moduli, 3 and 9, because they are powers of 3, right? And so, now, it turns out since 10 to any power is always equal to 1, if you just think of the decimal expansion of any number, it's the sums of a bunch of powers of 10s with coefficients. Well, if you replace those powers of 10 with 1, all you're left with the digits. And this SOD stands for the sum of the digits of the number. It's kind of neat. Now, this isn't a rigorous proof, but hopefully it's convincing to show that any natural number n is congruent to the sum of its digits, SOD mod 3, and any natural number n, not just this one, is congruent to the sum of its digits modulo 9, okay? Now, the hardest part here, if you want to call it hard, is actually figuring out what the sum of the digits is systematically without just writing it all down, you know? And so you can see, hopefully you can see where this comes from. This 3, this will give you an idea of the schema I use. This 3 right here, okay, and then this 1 right here, we're kind of the special case because notice that it ends in 31. It ends in 31, and you can hopefully can see where everything, 5 times 1 because there's 5 1s in the first digit, 5 2s in the first digit, all right, and then 3 is the last first digit of the odd numbers, and a similar thing right here. It's always going to be 1, 3, 5, 7, and 9 as the last digits, and there's 2 groups of powers of 10s if you want to think it that way. But in any event, it does sum up to 69, which is easily, it can be verified, slightly tedious, but not too bad. All right, now, so let's see how that helps us with regard to our problem here. So we know right now that our n that we started with up here at the top, the 22-digit number, we know that n is congruent to the sum of its digits, which is 69 mod 3 here. Let me erase that real quick. Okay, so, but that's congruent to 0, right? see 69 is a multiple of 3. It's 3 times 23. So we'll put mod 3 here. Okay. Now also we get that n is congruent to 69. Okay, now we're going to consider mod 9 now. So that would be congruent to 5 mod 9. And the arithmetic's not hard there. I don't think, let's see, is that right? Congruent, 69 divided by 9. 9 times 7 is 63, so we need actually 6 right here, right? Is that right? 9 times 7 is 63. That leaves a remainder of 6, yeah. So, y'all, this should be 6, sorry. Oh, let me just erase that again. All right, so erase. This is congruent to 6. Mod 9. Okay, so again, folks, the reason for this is that if you divide 69 by 9, 9 times 7 is 63, right? 9 times 7 is 63 with a remainder of 6. And you can think of congruent arithmetic as remainder arithmetic. When you divide 3 into 69, you get a remainder of 0. When you divide 9 into 69, you get a remainder of 6, since 9 times 7 is 63, right? Okay, so what this means is that this tells us right here, it's the very same thing as saying that 3 does divide in. Three has to be a divisor of n. And it's real clear, maybe I could have done this in a more direct fashion, but 3 divides n. But since we don't have a remainder of 0 right here, we see that 9, or 3 squared, does not divide in. And this will do this, we'll slash this thing. It's a negated relation. So 3 squared does not divide in. But now that takes us back to the result. There we go. So folks, now we just appeal to this result right here. If 3 squared does not divide in means it cannot divide any other powers, right? And so any other higher powers. And so we have shown that 3 raised to the first power this is, sometimes they call this divides exactly. The double, I don't know if you guys have seen this notation, but 3 squared divides in exactly. That means no higher powers of 3 divide in. This is something developed in Charles Vanden Eynd's textbook, and maybe others, but the double vertical bars means that 3 to the first divides in, and there's no higher power of 3 that divides in. So the answer to the problem, what was the original question? Determine the value of k. Okay, so this would say that k must equal 1. Okay. That's the highest power of 3 that divides that large number. So k equals 1 is the answer. And let me come back up and just put it in the, since I didn't manage to stay on the screen right here. So the answer right here is k equals 1. And again, it may seem like a lot of trouble, but I don't see any other way to do it really. You know, to write this number down and try to divide powers of 3 into it, you know, would be a pain, I think. So k equals 1 is definitely the answer here. And again, the modular arithmetic here came in super, super handy. Okay, thank you for viewing.